Good evening, everyone. Welcome to One Concept, Multiple Tools, Multiple Learnings video series. And this is my 11th video. So far, we had been doing videos on simulations, on what are the possible simulatory tools that are available for each concept. And towards it, we have already done for several tools. We have done 10 such videos based on graphs or maybe based on kinematic equations, SWOT equations, based on related to something like uncertainties, okay, then Newton's laws of motion, and then constant forces. The recent video which was uploaded today afternoon was related to variable forces. And now I'll be talking about the tools that are available for work energy and how do you use conservation of energy, what kind of tools can you use so that you would be able to showcase this particular thing appropriately, what kind of problems can be derived from there. So all this will be able to look into it. In fact, when I started looking into some of these tools, I remember some of the problems that were being asked in IB papers. Okay, I feel they had been directly taken from here, but here and there they have made some modification, I feel. So as a result of it, you got this one. So I feel that if you start using these tools, okay, on and off, then you might get an idea like how to prepare a question, or when such questions are being asked, how to get a solution for it, because you'll be able to visualize it. Okay, so if a question has been asked. Okay, now let us begin with it. Let me share my screen. So the first one is about the energy skate park. This, many of us had been using it. Even I, in fact, I also remember using it for my while I was teaching energy basics. I used it in ninth grade IGCSE, I think. Yeah, even if I in my MYP also when I was teaching this, I had used this. Right. So the first one is a very basic one. Then we have a friction and with a playground. So I just showcase this one. This is on PHET. So when I click on this, you see there's a skater here. There's a V-shaped one over here. And then what you can do is you can let me move this one downwards. Okay. Right. So what you can do is you can pick up the skater here, drop it to certain height, and then you can click on the bar chart or pie chart. When you click on the pie chart, as you see on the person, you can see there's something like a green color and a blue color alternating over here. The green color sector is related to kinetic, the blue color sector is related to potential, and there is no thermal energy because there's no friction over here. That's what you can see, no red color over here. Now, if suppose there was friction, unfortunately, we don't have anything to show over here. Maybe in the further ones we have this. Okay, now if I want to show, if I want to calculate the energies, the better thing would be to go for the bar graph. If I go for the bar graph and I click on the grids over here, click on the grids over here. Okay, so sorry, the grids is not seen over here anyway. So kinetic energy and potential energy keeps on alternating so that the total energy is the same. So as you see, the total energy is equal to maximum of kinetic energy or maximum of potential energy. Now this is true for the oscillations. This is a to and fro motion. So this is true even either for this one, or maybe you take a spring and make it oscillate vertically or maybe horizontally, or maybe a pendulum. Do whatever it is as long as the amplitude remains a constant. Okay, you observe that the energy will not change. It could be partly kinetic, or partly potential. It is like if you have a number 10, you can write 2 plus 8 equal to 10, or maybe 3 plus 7 equal to 10, 4 plus 6 equal to 10, and so on. So this is what you can do with it. Okay. So you can then later on, you can also do slow motion, you can do all this. One interesting thing is that, okay, so what I will do is I'll just stop here, and maybe I'll stop here, pull this fellow here, and I'll drop from here. And then I ask a question, will it go to the topmost point? Okay, and when I start here, you see, he oscillates only until this much. Okay, that means, so wherever I drop, it goes only until so much. Okay, this is without friction. Okay, then I can, if I want to restart it, I can refresh this, or maybe I can restart the skater and I can do this. Now let me go on to the friction. When I click on the friction, I have an option to change the friction. The slider was not there in the earlier one. Now you have this friction over here. So what you can do is you can, initially it has some friction. I'll take this fellow once again and drop him here. So what do you expect? We can ask the students. So as usual, now this will go on like this. It will not even go until here. Then it reaches here. Then it reaches here. Then reaches here. Then it slowly keeps on coming down. In other words, the amplitude keeps on dropping. And finally, he comes to a rest, right? And if you want to know how is the energy distribution taking place, you can click on the bar graph here. click on restart once again. Now you see the thermal bar also gets active. Now let me click on this. Initially thermal is 0. Then for every oscillation it makes, the thermal bar keeps on growing, which means that there is some amount of heat generated while the kinetic and potential keeps on dropping. It keeps on reducing. That's what we can see. Okay, let me go on to the playground. This is quite interesting. This I love to use this one. So what you can do is there are 3 points over here. You can just pull this one here, keep it over here like this. And then what you can do is take this red spot, drag it like this over here. And take the other one, drag it over here. And then put on the grid. Put on the grid. And then what you do is keep this one at this point. Maybe exactly here. At this point. Okay. And then what you do is take the skater once again. And then put him here. Now he starts oscillating. To what height it goes? It goes until this height. And then it keeps on coming down. Now what you can do is, I do this as a different type of exercise. Since it's a programmed experiment, so I ask the students to take a digital timer here. Okay, how do I take a digital timer? I can start something like this. I can go to space and then, I can go to Windows key, click on the Windows key and then type for clock. It's already there. You can just type it like this, or maybe you can say CLOCK. When you do this, you get something like a clock app. Okay, click on this clock app. And then once this is on, now it's 1:30, it's showing over here. So what I'll do is I'll click here. Oh, I'm sorry, not here. I'll click once again back to this. And I'll go back here and I'll click on stopwatch. Okay. And then I'll take this fellow here. Keep him here. I want this to be a model one. I'm sorry. Just a minute, wait. Let me keep it over here. Okay, now this is on. So I will keep the friction to be 0. I want the friction. Oh, if I sorry, I will not keep the friction 0. I want the friction to be some value. I'll keep it exactly in the middle. Okay, some value. I do not know what is the value. And now what I will do is I will take this person and then drop him here. Okay, and at the same time, I start this. Now count the time taken by him to come to a stop. Okay, I'll do 1 or 2 trials and then move on to the next one. Okay, so I get some value here. Let us say 10, 15, 14, 15, still going on. And of course, there is some reaction time here because it took some time for me to do this. This I assume this, or I asked them what will I do with this. Okay, actually I was supposed to start here, but the moment it started here, it came over here. I'll ask the students what will happen if this is the case. Right. It took 35 seconds. Next, what I will do is I'll take this spot here and then I will move from here by 2 squares. Earlier it was there. Now I keep it here. Earlier it was here. Now I kept it over here. Now repeat the experiment once again. Okay. I will then restart this. Keep this fellow once again here. Go back and then start this. Now once again, the question is that will it come back to 35 seconds? Will it stop at that point, or will it take less time or more time, or what is the reason behind it? This could be a wonderful exercise. In fact, if you are able to construct something for your IA and design it and ask them to do it, okay, and ask them to reason it as why does this happen, how do you calculate the time, and what parameters does it depend? Really a classic one. Okay, so many things that one can do just by looking at this. Is it that the time remains the same or will it change? It is 35. I made a bit late because the moment I saw this and clicked over here, maybe it would have come at 34. Let me do this let me pull this once again by 2 more, keep it over here and redo this. Oh, I am sorry. I need to restart this and then I have to do it. Let me redo it once again. I'll drop from here. Right. Let me see how much time does it take. Does it just depends only on the path length, or does it depend upon the velocity? So so many things are coming into it. So you will be able to ask them so many questions, and they are supposed to have a knowledge of the free body diagram, how to arrive at it. So many questions can be done using this. Okay, so like this, you can conduct an experiment which is quite novel, which is not seen in any textbooks or anything. So you can easily do this one here. So So here in simulation, almost it comes out to be the same. But in reality, see, it comes out to be the same. Okay, maybe it's a programmed experiment, so you might get the same answer. But in reality, does this happen? Now, if you want to do, how do you do the construction? You can ask these kinds of questions. Okay, now let me move on to the next one. Let me go on to the next one. I'll close this. Right. Now, this is just a replica of the same thing. But the thing is that they had only 3 points. They have multiple points over here. Okay, you can decide which one you want to use. This roller coaster. So there are points over here. You can change the points. You can keep this one to be completely low here, this one to be completely higher here, this one to be completely here, and here to be once again this much lower over here. And now ask the question, see, if I release this one from here, will it reach this point? Okay, on what basis do you think so? Because here it comes out faster, but the moment it comes here, it has to once again go upwards like this. Okay, so does it really come up or not? So what you can do is you can go down here, there is a run here, you can click on this, and as it comes down, you can also find out what is the amount of energy being spent. Okay, this was not available. This was not there. Okay, but here you can, it was there, but the value of it, okay, here also you can get the value. Okay, so here as you see, it starts oscillating like this also. Okay, now the question is, can we create such a terrain physically in the lab? Is it possible? Of course, it's not possible because there will be some amount of friction being seen. You can ask the students to design something very similar to it and what considerations they would like to do it. Okay, so many questions can be asked like this. If it was an MYP question, then definitely, okay, we'll like to go with it. Let me click on this trace. The trace tells you what are the paths, how does it go, and so on. But there's something which is shown over here. See, the dots are seen to be smaller here, then becomes larger here, then once again becomes smaller here, and the spacing between the dots is different. What does this tell you? You can ask this question. Okay, is it just dots which are being written, or is it something else? It's nothing but for consecutive time intervals, the distances traveled by the cart is being shown over here. So as a result of it, okay, whether it is getting accelerated, whether it is getting decelerated, where is it getting accelerated, these kinds of questions can also be addressed using this. It opens up so much avenues to understand about kinematics using such kinds of questions. Okay, the next simulation is very similar to this, the same one, again done by Java Labs itself. There are dots given over there. Since if I click on trace, I get this in here. The mass of the cart can be adjusted. Then when I click on this run, it's already running over here. Okay, so this is what you get. The height is seen to be at this point. There is no friction over there. So what happens is this cart is now made to come here. It compresses the spring and then it is going over here. So what does it tell you? That whatever energy it has, this energy is now given back to the spring, and as a result of it, it stores this energy in the spring energy, and then when it comes back over here, the spring energy makes it to go away from here, right? So the spring constant is given. You can ask the question, you can ask them to determine what is the compression without looking into the scale. Will they be able to find out what is the compression? What is the velocity at this point? Will they be able to find out using the compression half mv square equal to half kx square? Can we do that? You can also ask the question, why can't we use something like F is equal to minus kx over here? Okay, and if that is the case, can you find out what is the force acting here? You can ask a number of questions here, right? You can actually change the slope also. When I click the slope, okay, instead of the spring, I can put this one here. And if I remove this and I say I put the spring over here, I can actually change the slope here. See, I can change it like this also, right? Here, if I keep it at 0, I will not be able to push this one here. If I keep it over here, because there's no friction, definitely you can hit it over here. And then you ask the question, how does the compression change based on height? Now this becomes your IE, right? Okay, so like for example, for 0.6 meters height, okay, and for a given mass, then the compression can be observed to be, use a constant cart, the compression is observed to be how much? 2 point something maximum. What is the velocity? What is the compression? You would have observed from here, right? So now if suppose if I increase this by 0.1 meter, then what will happen? See, 0.8, if I do a 0.8, and then run this once again. Speed increases, the compression also increases. How does the compression change with height? Okay, maybe probably I would be doing this kind of experiment for this year's IA. So I can give it to my students, I can ask them to do it physically, have a spring, have an inclined plane, then do this one here. At the same time, verify it also using experimentally, and then ask them what is the difference between. Okay, so this one, okay, let me start this. Right. So this is about the second law of thermodynamics, but anyway, I would like to use it in a different way. So what we have here is that I have a pendulum here. and the air molecular density can be varied over here. Okay, initially it is 0, and then I can hit reset over here. There is a run command, run command, run command. I couldn't see the run command over here. Okay, run command, I can just pull this one here and leave it here. There's no run command. Okay, so automatically the pendulum starts moving up and down to and from motion C. Now what I can do is, I can now increase my air density. Once again, you can use my timer, ask my students to do it. Of course, you cannot do this as an IA. So you can see, you can ask them, okay, so what will happen to the pendulum if this is the case? Okay, it looks like our Tetris game, right? So this ball, this molecule, there's an air molecule, comes and hits here. Of course, okay, so each molecule comes and hits here. There are molecular collisions being seen. This is what happens over here. So some amount of energy is being taken over by here, and then it keeps on moving like this. And then I'll increase the molecular density. Now what will happen? More number of particles are being hit by the pendulum. So some amount of energy is being lost by the pendulum, but after some time, this comes to a rest. Now if the molecular density is much, much higher, we increase it. Now what happens? Many particles are being hit, so most of the energy, much of the energy is given to it. Now, if I increase it to a larger extent, now you see, definitely for every moment, for every 0.1 second, it has to hit something, and as a result of it, okay, so the energy gets lost. Okay, that's what it tells you. But how do you apply second law of thermodynamics? You can go through this one over here. So what is reversible, what is irreversible? So when the process which you get is an irreversible process. Okay, but is it possible that the molecules all come to a standstill and the pendulum also starts moving? Okay, so the things like this, arguments like this are being discussed over. Okay, next let me go on to the next one. The next one is about, right, so you have a pendulum, you have an incline. The incline can be changed like this by pulling it across. And then you have an object which is in a friction, which is posing a friction over here. Okay, or maybe it is now trying to obstruct it. What I can do is I can run this. The moment I run this and put a trace also, which means I tell you whether it is moving at uniform velocity or not. Click on this run. So what happens? So here there's an acceleration, and as it comes down, it's getting accelerated. When it reaches this point, you see the distance between two spots are same here, and then there's a deceleration here, right? Dots are coming nearby, and then it moves by a certain distance. Now what all can you find? You can ask the students to find out the value of mu, because friction is given to you, okay, and then the frictional force equal to mu times mg. M is given to you. M is not given. The reason is because there's a frictional force, there's a friction acted over here. Okay, maybe you can don't consider this as a block. You can say there's a friction acting here. Mu times mg can be equal to 100 Newton. Based on this, you can find out the value of mu. You can find out what is the velocity. You can compare this velocity. You can do many things over here. Okay, using the work done, you can do it, right? So work done is equal to how much? Work done is equal to 100 Newton multiplied by 2.94. You can use that, and you can find mu times n multiplied by the distance, which is nothing but the work done against the friction, and thus you can find out the value of mu. N is already given, n equal to mg, so you can use that and finally get the answer for this, right? Okay, so somewhere, see, simulations had already been telling this is not something like visually seeing something. Using whatever you see, okay, it blends your creativity, it enhances your creativity. From there, you should be able to extract some information, put it across in a spreadsheet, and then try to use it, okay, to derive some rules or maybe some patterns or maybe some equations or do something like this. Okay, it should not just be, okay, click something, move on, move down. Okay, that should not be the case. Okay, you should always have a paper and pen to start working on this. Next, right, we're going too slow. This one is about a spring balance and a graph. The graph is about force versus displacement over here. It's a spring balance over here. Now, as I pull it across, you will be, okay, let me refresh this. So I'll start from the beginning. Before I start, I just started to work on this to see how does it work. Okay, so that you can see some default values. So work done here is equal to 0. Now, initially, I'll start pulling it. And as I pull it, now what will happen to the work done? Now, let me say here it is the force meter is given here. Now, I'll start from here. I'll pull it. So what happened? I stopped at this point. Now what do you see here? The force initially increased, displacement was 0. Why was it 0? Because, now let me, so the force was 0 because maybe there could have been some friction or maybe it has some inertia. Definitely there is a friction, so you need to pull it across. Okay. And as you started pulling it over here, I stopped at this point. You can ask the question. You can start this graph. You can ask the students, okay, see, why am I getting a declining one? What did I do here? What was my action? Right? So these kinds of questions can be asked. If I still pull it once again here, see, once again, right? So I immediately applied a force. I applied a larger force over here, 2.5 Newton, and then I pulled it only for a very short interval of time, and then I released it. I did not do anything. And as a result of it, the force became zero. And how did it become zero? It gradually declined. Why did it decline? Because it is a friction, it's a spring. And whenever there is a spring, it doesn't come to a zero instantly, right? It is not like a thread. Difference between a thread or a rope and a spring is that in a rope, you have an object, you pull it across. Okay, the moment you stop pulling, the force immediately becomes zero. But in spring, it slowly becomes zero, right? So that is what happens. So you can understand, you can find out the work done by finding out the area over here. If I do it randomly, if I do it zigzag, okay, a chaotic one. See, this chaotic. See, I'm pulling it like this. What do you see? You get different peaks over here. Okay, so you can find out the area by making use of this. So you cannot use your force into displacement over here. You definitely need to use the graph over here to find out the area and hence the work done. We move on to the next one. All these are taken from Java Labs. So many applications you have. Okay, once again, let me refresh it. Now here, let me click on this also, force distance graph. Now what I do is I can pull it upwards over here. So this is a plot of height versus force. Earlier it was force versus distance. Now it is height versus force. Okay. Now what I do is I increase this potential energy. Slowly I increase, or maybe I increase it faster. When I increase and put it over here, so what do you observe? The force is fluctuating initially and then it came to a rest. And you see you got a curve, okay, like this over here. So it was very difficult for me to calculate what is the work done by me in order to pull it across. But what was the question over here? The question is that find out the potential energy of the object when it was lifted from here to here. Now, how you should have lifted this? Okay, you should have lifted it slowly. Why slowly? The reason is because when I lifted it faster, then what should be the answer? What is the answer I should get? Mg into h should be your answer actually. Okay, the work done by you in order to go against it is mg into h. But if you look at this here, your mg is nothing but the force. Are you getting a constant force over here? M is mass is constant. G is also constant. M into G should be a constant. But here you see, you're getting a different value here. Okay, because you did some work in pulling this object and there was a difference in kinetic energies and hence you got a different value. Let me redo this once again. Let us say, for example, I do it slowly. Okay, with a constant force. Whenever I am interested in finding out what is the potential energy of an object, connect it to a spring and slowly lift it up. Okay, so keep it like this. Again, I am changing. No, see, there's a lot of oscillation. I should not do this. Okay, if I lift it slowly, ask the students to do this. Okay, so that they lift it slowly and they get the value of the force. They get the value of the force multiplied by height. And ask them how much do they get approximately. What is the work done by them in each and every case? How do they measure this? Okay, so they get to know about how to conduct an experiment. It's not just doing something, but there are some intricacies. There are some constraints, and they need to do it like this one. Okay, this is where this experiment will be helpful for you. Next one. Okay, this is not related to this chapter, but anyway, I found out this one, and this is related to unit B, which is on energy conversions. Okay, say for example, when I pour water, say initially it looks like this. When you go to systems over here, so when the person cycles over here, it rotates a dynamo, and as a result of it, okay, there's a heat being produced, and this heat produces heats up the temperature of the water, and the temperature rises. Okay, so you can click on this energy symbols for lower class. These kinds of experiments would really be amusing. Okay, they would be very happy to work on this. See, I increase this, what happens? Energy is now given to it, and as a result of it, turbine rotates. Kinetic energy is given to a turbine, and you can also ask the question like, what is the type of conversion which is happening over there? Okay, so these kinds of questions can be asked, and thus you see temperature is rising. Okay, in fact, you can substitute this temperature rise because it's not seen up to that very clear. Of course, this temperature rise is being seen here. You can either do this one, or maybe you can put a bulb here. You can put a bulb over here, okay, and then make this fellow zero initially. It is not glowing, and now, oh, it's not compatible with it. And maybe I need to reset this. And I will connect it here. Let me run this. Now you see, the bulb is glowing over here, right? So you can do these kinds of things also. Okay, let me move on to the next one. Okay, this is a very simple one, but it helps you in energy conversion. How can one energy being converted into electrical energy and so on? Okay, you can use it for a solar panel, you can use a cycle, you can see a turbine generator, water generator. So there is something like this over here. You can pull it across and you see there's a water falls onto it, the turbine rotates. For lower classes, it's very much useful to look into it. Okay, let me move on to the next one. Mass on a vertical spring. Now what do we observe here? The mass can be adjusted to 10 kgs or 10 grams or nothing is given over here. So this tells you that as the spring starts oscillating, how does the kinetic energy, potential energy changes, and what is the mechanical energy, and that is what it tells you. Okay. Okay, I got this. Okay, so current values are shown, this value is shown over here, and there's some amount of friction over here as the object starts moving. So the force is 20 Newton, constant force has been applied in this direction. It's not, okay, the first option gave you the first direction, horizontal direction. This is in a given direction, different direction over here. Initial velocity is 0, mass is 2 kg, coefficient of friction is 0, direction of the force is 30 degree above the horizontal. Now, what happens to the kinetic energy? That's the question. So when I play on this, now what do you see? You see that the kinetic energy keeps on increasing, but it goes much slower. So if you really want to understand this one, so what you need to do is, so the total energy here is going to be 609 seconds over here, 609 joules over here, and the final velocity it reached was 24.7 meter per second, and distance moved is 35.2 meter. Make a note of this somewhere. Now what you do is, you can also look at the kinetic energy versus graph. This is how the kinetic energy increases with the speed, because kinetic energy is equal to half mv square, so it should be nr linear graph. Okay, now let me go back with this closed graph, and I will go back with this one here. I wanted to see the previous one. Where do I go back? I go back here, work on kinetic energy, launch interactive, and when I come down here, I go to start, put on the force. So there are three ways of doing this experiment. The first one is put on the force in the forward direction. The second one is at an inclined angle. The third one is opposing this. Let me clear this one here. If you want to understand the second one, you need to do the first one first. Okay. Now, as you see here, the same parameters, no change in parameter over here. And then let me click on play. It was 609 joules over here in the kinetic energy. Let us see the final kinetic energy as it crosses the same distance. It has increased, right? The same distance, it has increased over here. Velocity is also over here. The same mass. So why does this happen? Because the force that you gave over here, okay, was inclined. So some part of it reduce your normal force. Okay, so that should be, okay, the answer. So you should be expected from this student. Okay, then you can change the values over here. You can change the force, you can change the mass, you can change the initial velocity, you can change the coefficient of friction. Let's say I change the friction to 0.2 over here. Let's try it. The same one. You can now view the thermal energy also. Now let me start with this. Now you can ask the question, like as you change the friction, what is the final velocity the object achieves? What happens to the energy loss? How much is the energy loss, right? So that also you'll be able to get an answer. Thermal energy seems to be 138. Now let us go to view to state chart. So this is the state chart over here. Kinetic energy was 0, total energy was 0. Kinetic energy final is equal to 0, total energy final is equal to so much. Okay, so like this, you would be able to arrive at these things. Okay, let me move on to the next. Now let us start with this simulation. The simulation is quite interesting. Okay, initially when we start with this, we'll think, hey, what is this? Something new. Okay, now let us start with this. So I kept initial velocity to be 0.6. The object is kept over here, and x naught is equal to 30 meters, 30 centimeter, 30 centimeter. It is distance is so much. Let me pull this one. This is the minimum. Okay, and tempo is 0.0 seconds, which tells you what is the time it has to record. Mass is 1 kg. Spring constant for this given here. G value, it's conducted to earth. There's no friction. Then the height of this is equal to 3 meter. Okay, so 3 meter. And then scale, accelerate, there's no accelerator over here, there's no engine being kept over here, maximum height, energy, and so on. Okay, let me run this. How do I run? I run here. Okay, it's going at 0.6. Oh my god, minus 0.6, it'll be very, very slow. Aha, so we need to go really faster, man. Otherwise, we need to wait for a long time. Okay, let it run. So now the question is that, will it be able to climb upwards? Okay, that's the question, right? Will it be able to, because this height is 1.4 meter, will it be able to go from here, climb upwards against the gravity and reach this? It definitely cannot, right? Let us view this also. See 2.1, 1.3, 1.1, 1.5. That's it. It stopped here, it came back. Now, in order to make it climb, what do I do? So I will now stop this initially because there's no friction. Once again, it comes to that point. Okay, now what I'll do is I'll increase this velocity. I'll make this velocity to be, you can't restart. I'll increase this velocity, make it to be around 3.1 meter per second. Okay, and now let me restart this. And let me increase it to a little. Okay, 3 meters per second will do it. When I do this, what will happen? It goes down. Many of the students will argue saying that this height is 1.4 meter, this 2.5 meter. So definitely a potential energy of this object is lesser. It will not go upward. But they should also understand, though it has a potential energy, lower potential energy, it also has higher kinetic energy. So as a result of this, oh, it went until that and came back. Still, it was not sufficient for it, right? Let me restart this once again and increase its energy by increasing the kinetic energy. Let me make it as 5.3 meter per second. Now, when I start this, now what can happen? Do you think this will go up? This definitely has to go up. Keep on an eye on this one here. 3.2, 2.8. Yeah, so it reached this point. Now it is going upwards. It goes here. It hits the spring. And does it compress the spring? So the speed is same. It has some kinetic energy. The kinetic energy is given to this. It compresses. To what extent it compresses? There's a compression over here. So find out whether it matches half mv square equal to half kx square. Determine the value of x, whether the value of x matches with it. Okay, if it matches, no energy has been lost. Else some amount of energy has been lost. Now it comes back here. Velocity is higher here. Okay, you can find out what is the energy at this point, what is the energy at this point. You can do all these things. What is the total energy? Is the energy conserved? You know, so many questions I'm asking. You can do all this, right? Okay, and thus you'll be able to solve a problem based on this. You can add some good examples over here. You can say this movement in a plane, this compression spring, that's what we are doing over here. Descent without spring, you can do this. You can click here. You can say springless climb. So whether it will be able to climb upwards, so what is the energy that you need to put it across? And if suppose, if I increase the height, see, there's one more thing that you can do it, right? If this was a height, what is the velocity? This was the height, what is the velocity? There's nothing but conservation of energy. Okay, you can ask them to experimentally find out whether your COE principle is being applicable or not. Then in a similar way, you can do spring descent, spring climb. Spring climb is what we had seen earlier, but with two, this one. And then you have spring descent. Okay, so this is seen. And then you have spring climb, valley with friction. Okay, when there is a friction, then what is the amount of energy being lost? What's the amount of energy being lost? And then you can also do ascent in 3 levels. Okay, so there is a friction here, and as it climbs up this one, it also has to go upwards. So you can do lots of examples like this, right? Okay, let me move on to the next one. This one is about a trampoline. Okay, how does the energy exchange takes place in case of a trampoline? So when I start with this, it is like this. Okay, let it load, right? Okay, the jumper mass is given here, the initial height, medium, all this is given here. You can actually get to know about, it's just an animation being shown about, okay, how does the total energy, the kinetic energy, potential energy, how does it vary as the person jumps across in the trampoline. Okay, in fact, you can change all this also. You can change the sliders and make them understand how does it work with it. Let us go on to the next one. This gives you some worksheets which we can actually give it to our students, ask them to work on it. Okay, which would be very helpful for them to do their IA or E if they take up something like this. Okay, how to write a report, what is that you expect in a report, what is the math behind it. Okay, you can get behind to know all these things. Let us move on to the next one. So there's also one more, which is once again a worksheet. So I have not designed any worksheet. These are all available from the websites. So one can just go to this website, download it, and you can use it however you want. Next, this is a video which shows about how does this work. This is in some other language, not in English. Okay, so maybe in French, I think. So if you know this, then definitely you can do it. And otherwise, the same video, there's a flash animation in some web browsers. It works. A morning, it also did not work for me, but later on 2 or 3 times I tried, and later on started to work with me. And this shows something like this over here. This shows you there is an object over here. There's a mobile undergoing only little friction over here. Okay, and this is 364 grams. There's a cart kept over here. And when I click on the start, this person removes his finger and then it starts moving like this. Why does it move? Because there's a weight over here. So this height is 0.36 meter. As the object comes and hits over here, okay, and then the tension in the string becomes 0, and as a result of it, it starts moving like this. Let us click on this. It becomes 0, the string becomes start, and it moves over here. So here this gives you about the position versus time for this object. Okay, so what is happening over here? There's an acceleration initially, and then it moves with an uniform velocity. And look at this over here, speed time graph over here. For this one, this is about initially there is an acceleration, then it moves with a uniform velocity, and then suddenly velocity becomes 0. This is for which one? This is for this cart over here, right? Initially there is an acceleration because there is a pull, there is a force, and then the moment the string becomes start, automatically the velocity becomes a constant, and the moment it comes and hits over here, the velocity becomes completely 0. Suddenly it becomes 0, right? And the force. So in this region there is a force, okay? But after that, what happens is the force becomes completely 0, right? Because there's no tension, so it becomes 0. So like this, you can do this in a slow motion also to make this one run and get to know how does it work with it. Okay, a wonderful simulation to begin with. Maybe you can do this as an IA also. So what kind of sensors you need to use, what is your independent variable, dependent variable. You can think about it and ask your student to work on this. So really good one. I'm planning to do something like this also. Right, next. Finally, a GeoGebra one. Any simulation that you take without a GeoGebra, there's no simulation, I think. Okay. There are many people who have been working in GeoGebra, lots of simulations available. Now, what is this simulation about? This simulation is about a two-dimension one, wherein you have a particle which is being kept at a height, and from here you are dropping this, and as a result of it, finding out the velocities, and also finding out the work done. What is the total work done with the particle? Initially, as you observe over here, so you'll not be able to see because it's very small. I don't know whether you'll be able to make it bigger. I don't see how do you make it bigger, but anyway, I'm sharing you the URL. You can go through this. Like this. I was able to make it bigger. Okay, so it's like this. When I click on the play over here, as you see, the object shows a two-dimensional one. And as the object keeps on going downward like this, you see your Wx and Wy will also change constantly, right? Why do you get Wx? This is the work done due to x-axis. Okay, Wy, the work done by the particle due to its fall along the y-axis, and that is along the movement along the x-axis. And sum of these two will give you the total work done by the particle, because we have been learning only the work done due to a particle moving in a single plane, okay, single line, one dimension. So this gives you the particle moving in a two-dimension. Okay, that's why I use this also. Three-dimension you don't have it, but this can definitely be asked. Okay, how do you find out this one here? So the total work done can be calculated like this. And you can always ask me a question, why in case of forces you use F is equal to square root of Fx square plus Fi square. But here you don't use the square over here. The reason is because work done is a scalar. You can ask this question and try to get an answer from the students. Okay, so with this, I think we have come to an end to what all possible simulations one can actually do using, I missed something over here, just a minute. Right. Okay. So what all possible simulations one can do using simulations, using work and energy. I have not touched upon the power over here. I couldn't find any simulations related to power and efficiency. Maybe in my next video, I will try to focus on that also. If I get something like this, I will do it. Or otherwise, the best way to use power is that you can use the timer as I shown to you. Okay, pull the timer there and then start the timer. But the problem is it may not be accurate because it's a programmed experiment. Okay, whenever it's a programmed experiment, so definitely, okay, so it is written not according to the laws of physics, or maybe it is written. I can't say it is not written. Um, but I do not know like how it has been written or what they have done. I'm not a coder, so as a result of it, I don't trust it so much. But to get the data, see, if the program already has a digital timer into it, you can always trust it. Nothing wrong. Okay, I'm not against any simulation because I myself I'm a simulation man. Okay, my entire PhD in bioinformatics was completely on simulation, so nothing wrong. But if I want to use a different tool apart from using this one, then I think we need to be very careful. Okay, so if it has been done by the same simulator, then it's fine. Fine. So let me stop here. So do like, share, and subscribe to my channel so that the YouTube also recognizes this and I get a lot of appreciation or maybe recognition, and it reaches worldwide to everyone. Thank you everyone.